All right, so in this next video, we're going to look at a couple more substitutions that'll help us solve ODEs that take a specific form. So the form that we're going to be looking at here is something that we call a Bernoulli equation. Take a look at this equation here. If I were to get rid of this y to the nth power here, what we have is a linear equation that's in the form that we would want it to be in if we were going to use integrating factors. So that should look really, really familiar from section 2.3. The difference now is this f of x on the right-hand side is being multiplied to y to the nth power, where n can be any real number. This is something that we call a Bernoulli equation. They show up in various different applications, and we solve them using this substitution right here, u equals y to the 1 minus n. Rather than derive that substitution for you and show you how it helps us solve these DEs, I want to just go to an example and use it and see what we can do with that. So here is our differential equation that we want to solve. I can see that it's Bernoulli because it's of the form dy dx plus p of xy, where p of x in this case is -1, equals e to the x, some function of x times y to a power, y squared in this case. So that substitution that was suggested on the previous page is y to the 1 minus n, or 1 minus 2 in this case. That's equal to y to the -1 power, or 1 over y, if I want to write it that way. Now, in order to make this substitution useful, I need to be able to substitute something for these y's in here to put them in terms of u. So let's solve this for y. That tells me that y is equal to 1 over u if I take reciprocals of both sides. Okay, so that means I'm going to be able to substitute 1 over u in for my y's here. But I also have a dy dx showing up here, and I have to deal with that somehow as well. I'd like to figure out how to come up with a du dx that relates to this, allowing me to substitute something back in there. So the way I can do that, let's use this right here. U is equal to 1 over y. I don't know the function y of x. If I did, we would be done at this point. So what I want is to take a look at what du dx would look like and think of it in terms of the chain rule. Du dx is the same thing as du dy times dy dx. Okay, but and that's true because this is just the chain rule in Leibniz form. Now, do we know du dy? Well, actually we do, because here I have u given as a function of y. So this is just the derivative of this with respect to y. That would be -1 over y squared. And then this dy dx here I don't actually know. But if I solved this for dy dx, that tells me that dy dx is equal to -y squared du dx. Now I have something that I can substitute for that dy dx, but I still have this issue where y is showing up. That can be dealt with by substituting y equals 1 over u into this expression. So this is equal to -u to the -2nd power, du dx. Okay, just making that substitution here in for that y. So let's rewrite our DE in terms of u's and x's now. dy dx is equal to -u to the -2nd power, du dx. So that becomes this. Okay, minus y, which is the same thing as 1 over u. Let me actually just write that as minus u to the -1 power. That's equal to e to the x. Now, y squared. What is y squared? Well, if y is equal to 1 over u, or u to the -1st power, then y squared is just u to the -2nd power. Okay, so making those substitutions, that's what I get out of that. All right, now let's do this. Let's first of all recognize that this looks very similar to a linear equation in u. So what I'm going to do is get this coefficient to become a 1. I'm going to multiply both sides of my equation here by a -u to the +2nd power. That'll turn this into a 1, giving me du dx equals, plus u equals negative e to the x power. Okay? Now we're looking at a linear equation where the p of x this time is just 1. I can use an integrating factor here. My integrating factor, mu, is going to be e to the power of the integral of 1 dx, or just dx. That's the same thing as e to the x. I'm going to multiply both sides of this by e to the x. E to the x du dx plus e to the x u equals negative e to the 2x is what I would get on that right-hand side. Okay? Now, remember, this is dealing with a linear equation using an integrating factor. This looks like the product rule, so we condense it down and we write d dx of e to the x times u equals negative e to the 2x. Integrate both sides. I'm going to get e to the x u equals, if I integrate that, the integral of negative e to the 2x dx, which is the same thing as negative 1/2 e to the 2x plus c. Divide both sides by e to the x so that we can isolate our u. I get u equals negative 1/2. This will now just look like e to the x plus c e to the negative x. Notice we have a transient term here, just to bring that terminology back. Finally, I don't want u. The variable substitution was only there to help me put my differential equation into a form that's more easy to solve. I need to put my y back into the equation here. Y, remember, was the reciprocal of u, the way that we defined it. So I can say that this is 1 over y equals negative 1/2 e to the x plus c e to the negative x. Let's solve for y by taking the reciprocal of both sides. Y is equal to 1 over negative 1/2 e to the x plus c e to the negative x. And I can simplify this by multiplying everything by 2 or a negative 2 to get that denominator out of the way. I don't really care to do that much with it. I'm pretty satisfied just with this. Okay? So this is the solution to the dE that we came up with. And again, it was Bernoulli, and so the substitution we wanted to make was u to the y, or u equals y to the power of 1 minus n, n being 2 in this case. Okay? And then inevitably what that's going to do in any Bernoulli equation is give you a linear equation that you can solve using integrating factors. Okay? So that was a fairly straightforward one. It was a little bit simpler than the last example, I think. We have one more type of solution that we want to look at now. This time we're looking at dEs that take this form. dy dx equals some function of a linear expression in the two variables x and y, f of ax plus by plus c, okay, where b is non-zero. That means that this y term needs to be present there. When that is showing up, or when we have a dE that looks like this, we make a substitution, u equals ax plus by plus c. The whole thing that we're seeing in the argument here, we call that u. Okay? And this will take our dE and reduce it to a separable differential equation, our favorite kind. So one example left to look at. This one's going to be an IVP, just to make sure we're continuing to do IVPs. The function is dy dx equals 3x plus 2y over 3x plus 2y plus 2. This expression in the denominator here is taking that form that we were talking about, ax plus by plus c. And this expression up here looks very similar, so that denominator suggests what my substitution should look like. I'm going to set u equal to 3x plus 2y plus 2. Okay? Now, in my in my differential equation, I have this dy dx appearing here. But how does dy dx relate to du dx? Because I want this to turn into a du dx somehow. Well, let's first figure out what du dx actually is. I'm sorry, we can't do that. Du dy, that's what I meant to say. If I evaluated du dy, okay, I'm sorry, not du dy, du dx. I don't know why I'm getting my variables mixed up here. We're integrating this whole thing with respect to x. So that becomes 3 plus, think of this like implicit differentiation. Y is a function of x, and I'm differentiating it with respect to x. That makes this 2 dy dx. Okay? So du dx equals this. Now, if I solve this for dy dx, I'm going to get dy dx equals 1/2 du dx minus 3/2. A couple of steps to just algebraically solve that. Okay? Now, let's see. What do I want to do next here? Are we ready to make some substitutions? I think so. So for this dy dx right here, we want to substitute this expression. My dy dx becomes 1/2 times du dx minus 3/2. Now over here, this side becomes much simpler. My denominator was just u, right? What about my numerator? Well, my numerator looks like my denominator after subtracting that 2 away. That means my numerator is u minus 2, okay, which is fairly easy to solve. Let's get this du dx by itself here, so I can multiply both sides by 2, add this term over. I should get du dx equals 3 plus 2u minus 4 over u. Okay. Now for this, for the purpose of the separation of variables that's going to happen, I would like to combine these into a single rational expression. So 3 is the same thing as 3u over u. Combine that with a 2u here to get 5u minus 4 over 2. Or sorry, over u. Over u. Separating variables now. Using these two sides here, this is the same thing as u over 5u minus 4 du equals dx. Okay? And so this is the guy that I want to integrate both sides on. Like this. Now to integrate this, I'm actually going to make another variable substitution. I can't call it a u substitution because I'm already using a u. I'm going to call it a v substitution. I'm going to set v equal to my denominator there, 5u minus 4, which implies that dv equals 5 du, or 1/5 dv equals du, so I can make that substitution for the du here. In addition to that, I know that with this substitution, my denominator down here can be now written as v. What do I do with my numerator, though? Well, I'd like to solve this thing here. So solving this for u is going to equal v plus 4 over 5, solving that guy for u. So that is going to be substituted in for the u up there. That means that this side is going to look like the integral of v plus 4 over 5 over v, okay, dv, and then I also have that 1/5 that's in there, so I'm going to call that 1/5. Let me pull this 1/5 out. That's the same thing as 1/25 times the integral of v plus 4 over v, which can be written as 1 plus 4 over v dv. Was it 4 or is it 5? Oh no, I've got the right thing there. Okay. So then with that, I can do the integration here. This is equal to 1/25 times v plus 4 natural log of v, absolute value of v here, plus, well, I'm not going to do the plus c because remember this is just the left hand side of this dE up here, and we usually put the plus c over here. substituting what my u was equal, or substituting what v was actually equal to, this is the same thing as 5u minus 4 plus 4 times the natural log of the absolute value of 5u minus 4. Okay? So that, rewrite it over here. Actually, let me substitute back what u was equal to now, because I have u in here. U was equal to 3x plus 2y plus 2. So this whole thing is going to get pretty messy, but we'll simplify things down. This is equal to 1/25 times 5 times 3x plus 2y plus 2 minus 4. So I made a substitution for that u right there. Plus 4 times the natural log of the absolute value of, equal to that, 5u minus 4 right there. Okay. So I did all that work to get this thing back down to, sorry, I didn't want that to be in terms of u anymore. 4 natural log of the absolute value of 5 times 3x plus 2y plus 2 minus 4 in there. Like that. Okay? Yeah, it's a huge mess. That's fine. We're going to simplify things down a lot. But going back to what all of this was in the first place, it was working with this dE up here. Okay, so I did this integration, and after doing all that integration, putting everything back in terms of x's and y's, I got down to this right here. I'm going to, in the next step, rewrite both sides of these after integrating, and I'm also going to simplify all of this stuff down by combining x's and y's and all that good stuff. So what we're going to get now is 1/25 times 15x plus 10y plus 6 plus 4 natural log of the absolute value of 15x plus 10y plus 6, that's after simplifying the previous step that we did, is equal to the integral of dx here. Couldn't ask for an easier integral. That's x plus c. Okay? Now at this stage, we would like to substitute our initial condition in. Initial condition is up here, y of -1 equals -1. So we're plugging -1 in for x's and y's here. 1/25, 15 times -1 plus 10 times -1 plus 6 plus 4 natural log of the absolute value of 15 times -1 plus 10 times -1 plus 6. Boom, like that, equals -1 plus c. There's a lot to solve here, right? There's a lot of arithmetic. I'm going to skip all of that arithmetic for the sake of time. I know that you're able to do that. So this, solving for c, we end up with c equals 6/25 plus the natural log of 19 over 25. That's, the natural log of 19 is going to come out of this part, and I'm not going to plug that into a calculator. I just want to leave it in terms of the logarithm there. So if I plug that in for my c, and then also I can, if I were to distribute this 1/25 in here, subtract that x over to combine it with the x over here, after a lot of algebra and whatnot, we end up with this as our solution. -10x plus 10y plus 4 natural log, the absolute value of 15x plus 10y plus 6 equals 4 natural log of 19. So we cleared denominators here, and we combined a lot of like terms and all that fun stuff. We should have ended up with something that looked like this. Now this one was a pretty cumbersome one to work with, and the reason why is because the substitution that we made was this big expression. And then not only that, that u ended up in an integral where we had to make another variable substitution. So we went to a v, back to a u, which took us back to x's and y's, and it got really messy, and we had to plug in some numbers for our initial condition, and that was a lot of arithmetic, and we skipped a lot of that. And again, that's just sort of the nature of this class. There are some areas of math where where a lot of the work is very elegant, very you get there kind of quickly, and then there's differential equations where it's a lot of drudgery and not to put down the subject, but a lot of it feels that way. So this is our solution. This is an implicit solution. I'm not going to even attempt isolating the y here because of that natural log. You're going to run into some problems. So that's totally fine. Remember, we're usually satisfied with an implicit solution if an explicit one is just not really practical. Okay? But that's going to wrap up section 2.5.